In this lecture, we're going to look at a really neat type of recursively defined sequence called a discrete population model sequence or logistic map. The sequence is fairly straightforward to understand. We need a seed, so x naught will be the seed of our recursively defined sequence, the first value in the sequence, and we have to choose that between 0 and 1. We're going to want all of the terms in our sequence to live between 0 and 1. Once you have that seed, you plug it into this recursion. x1 would be a times x naught times 1 minus x naught, x2 would be a times x1 times 1 minus x1, etc., where a here is some parameter that's going to be chosen to be positive. This map is called a quadratic map because if you look at the right-hand side, it's really like a quadratic expression on xn. In fact, for shorthand, let's define a function capital F of x to be a times x times 1 minus x. That's a degree 2 quadratic polynomial. Here's the graph of f. If we assume that all of the values in our sequence live between 0 and 1, the only part of the graph of y equals f of x that we'd be interested in is this arch right here from the origin over to the point 1, 0. We can rewrite our recursion as x sub n plus 1 equals f of xn. Right, so to compute the next term in the sequence, you plug the previous term into this function f, which means that if you wanted to figure out what x sub n plus 1 is, if you knew what xn was, say xn was right here on the x-axis, xn plus 1 would be f of xn. So you plug it into this function, and your next term in the sequence would be the y value of the corresponding point on the parabola. Just like this picture shows, if you plug 1 into the function, you get 0. And if you plug 0 into the function, you also get 0, because here are the x-intercepts of this parabola. So typically, we will only really assume that our seed x naught is strictly between 0 and 1. The maximum value of this parabola occurs right in the middle of the domain, so right at x equals a half. This would be the largest possible term in the sequence, right? This is the highest y value of all of the possible terms in the sequence. We want our sequence terms to be between 0 and 1, so let's figure out how high we can get. If we plug 1/2 into the function, the result is a divided by 4. Therefore, if I want all of the terms in my sequence to live strictly between 0 and 1, I need to make sure that this parameter a is not only a positive number, but it's also a number which is less than or equal to 4. Whenever we have a sequence like this recursively defined sequence, one question is, does the sequence converge to a limit? So if I start to write out what we will call for this type of sequence the orbit of the seed x naught, we start with x naught, then we go to x1, which is defined to be a times x naught times 1 minus x naught. Then we go to x2, which is a times x1 times 1 minus x1. And we keep doing that. So the question is, if I compute out all of these terms, do they trend towards some limit L? And it turns out that the existence of a limit is going to depend on this parameter value a. We have 3 different regimes for a, so let's talk about first if a is between 0 and 1. Well, let me consider the terms x1 and x2 that I wrote over to the right. So we said that x1 was a times the seed x naught times 1 minus x naught. But our seed is between 0 and 1, so 1 minus the seed is less than or equal to 1. So that means that x1 is less than or equal to a times x naught. Similarly, x2 is a times x1 times 1 minus x1, which we can say is less than or equal to just a times x1. But x1 was less than or equal to a times x naught, so now this is less than or equal to a squared times x naught. Continuing in this way, we can see the sequence term xn is going to be less than or equal to a to the n times x naught. Since the parameter a was between 0 and 1, a to the n goes to 0, which means that our terms are shrinking, and so the limit is 0. So anytime our parameter value is between 0 and 1, we know that the sequence will shrink to 0. For the next case, suppose that 1 is less than or equal to a is less than 3. We're not going to prove it here, but it turns out that this sequence will also converge to a limit. Let's call it L. We can compute what L is. So if we write down our recursion, let me write down the left and right hand sides. As n goes to infinity, all of the terms from the sequence, x sub n plus 1 and x sub n, they're all going to go to the limit L. So we can think of the left-hand side of this equation as going to L, and the right-hand side of the equation as going to a times L times 1 minus L. So that gives us an algebraic relationship for the limit L. We can say that L equals AL times 1 minus L, and then we solve for L. Let's see, first I can cancel out L, and then if I isolate the remaining term, we're going to get L equals 1 minus 1 over A, and then that's often written A minus 1 divided by A. We can call that X bar. Notice if A equals 1, X bar actually equals 0, so you could kind of roll that into the first regime if you wanted to. Now we didn't do the proof, but we're just assuming here that if we're between 1 and 3, the sequence does converge. The proof we would use to show that breaks down for A greater than or equal to 3. In fact, when we look at the behavior of the sequence for A greater than or equal to 3, we're going to see lots of different types of behavior. These sequences are fun to work with because there's a really neat way to visualize what the terms in the sequence looks like. We already saw that parabola f of x, which tells us what the types of values that we would find are using the recursive definition. So let's kind of track where those values live relative to this parabola. Okay, so here's that parabola, and in this case, A equals 0.85. It's not labeled here, but the leading parameter A is 0.85, and I'm going to choose an initial value of 0.9. So here's the first term in my sequence, the seed of my sequence, and what we'd like to do is discover its orbit. Well, what we've already said is the next term of the sequence is f of x naught, so essentially you want to take that value and plug it into your parabola. The corresponding y-coordinate is the next term in the sequence, which we call x1. The thing is, I would like to now plug x1 into the parabola, but I can't plug in off of the y-axis. That doesn't make any sense. So what I need to do is figure out where x1 lives on the x-axis. So to do that, I'm going to reflect that point over the line y equals x, kind of bounce it down to the x-axis. So we form a sort of perfect square down in the bottom left corner of this picture to bounce that y value down to an x value. At that point, we can plug it into the function capital F of x and figure out the corresponding y value on the parabola. That gives us the next point in our sequence, x2, which we then bounce off the line y equals x. Now plug that into the parabola, get x3, bounce it down, etc., etc. So as you can see, the terms in the sequence start here at x naught, and then they're traveling to the left. Okay, so the actual values in the sequence would just be the values that you could read off of these points on the x-axis. We have x naught, x1, x2, x3, and we're going to be coming in towards 0. Let me do this one more time with a different seed. How about a seed of 0.6, and I'll do a as 0.99 just to make it a little taller. Okay, so here's our new parabola. This time a is 0.99. The next value in our sequence would come from plugging that into the function. That y value is over here, that's x1. I need to plug it back into the function, so I've got to bounce it down to the x-axis. Plug that in, get the corresponding y value, bounce that down to the x-axis again by reflecting over the line y equals x, and we keep doing that a few more times. Okay, we've got a lot going on in this picture, and what we're going to do is reduce it so that we're not looking at quite so many lines. Notice the convergence here is happening kind of through this zigzag pattern. In fact, we don't really need all of this vertical line right here. All we really needed to do is figure out the point on the parabola where we would land. So instead of going all the way down to the x-axis, let's stop when we get to this parabola. Likewise, we don't need to go all the way over to the y-axis. We just need to figure where we bounce off the line y equals x. So let's stop doing all of these lines and make this kind of shape instead. This is called the web diagram. So we figure out our seed, we go up to the parabola with the seed, and then from the parabola we go straight horizontal to the line. From the line we go straight down to the parabola, or straight up, it could be. Okay, so we go straight vertically to the parabola. From the parabola we go horizontally to the line, then vertically to the parabola, horizontally to the line. And the idea is that this new shape tells us the behavior of the sequence without kind of all this extra stuff. Now that we've seen how this web diagram is created, let me show you the types of visualizations that we'll look at for the rest of this lecture. So instead of going through this step by step every time, what I'm typically going to do is show you just a movie. Okay, so this movie shows the creation of the web diagram for a equals 0.75 and x naught equals 0.45. As you can see, we get kind of funneled down towards the origin because our web diagram gets trapped between the line and the parabola. Let me do another one where a equals 1. What's special about the value a equals 1 is when a equals 1, we really have tangency between the line and the parabola. You can see the convergence didn't quite happen as quickly as in the previous example. Up until a equals 1, though, the line sits on top of the parabola. After a equals 1, the line is actually going to be under the parabola at the origin. So let's look at, how about a equals 1.5? With a equal to 1.5, you can see that we have two intersection points here. And for this particular initial value, what we did is similar to before. So we kind of came above the parabola and got trapped towards this intersection point. Let me show you a few different initial conditions. So how about 0.95? Okay, there we actually get trapped from the left. This is a new behavior we haven't seen before. If I just started over there on the left, I'd stay in that trapped area. Okay, so if we come at it from the left-hand side, kind of get trapped up to that intersection point. If we start over on the right-hand side, we bounce over to the left, at which point we are trapped, or we could come in entirely from the right. But what we start to observe in all of these situations is that convergence is still happening. It's just not converging to the origin, it's converging to the second intersection point. Let's look at a few simulations with a equal to 2. So let me change the a value. Well, if a equals 2, the intersection between the parabola and the line happens right at 1/2. So if I pick an initial seed of 1/2, I'm actually right at the limit and we wouldn't move at all. If I pick something like 0.75, then we see the same behavior as before, where we bounce left and then travel up. If I pick something that's from the left side, of course we just travel up to that intersection point. And here what you can see is actually those are the only two types of behavior. So you either start right and bounce left, which is what we did in this picture, you have to really zoom in to see it, or you start left. There's no kind of converging to the limit from the right like we had in the previous regime. Let's now look at a equals 2.5. Here we see a new behavior. We haven't seen this kind of spiraling action before, so this happens for a values larger than 2. Let me try a few other initial conditions just to give you some pictures. Okay, there you see we come at it from the left, but instead of staying trapped between the parabola and the line like we did up to a equals 2, we're now actually trapped for a while and then we spiral. If I start way on the right, of course I bounce left and then I spiral. But one more simulation with a equals 2.99. Here you can really see the spiral action because the convergence is quite slow. In fact, we didn't really get there, so let me increase the length of the experiment. So as you can see, we're going to converge into that middle point, but pretty slowly. All right, let me run a simulation now where a is 3.2, and just to have an initial seed, I'm going to pick x naught to be 0.1. This sequence is going to create a web diagram for 100 terms, but after a while you won't really see any difference in the web diagram, so it'll be hard to tell that anything is happening. The simulation is not over until you see the phrase simulation over at the top of the diagram. So if it doesn't look like anything is happening but you don't see those words, technically the web diagram is still forming. Okay, so now you can see that this web diagram, and here I'll start running it again as I'm speaking. This web diagram, kind of like in the case when A was between 2 and 3, orbited around the intersection point, but it didn't converge like it did for A between 2 and 3. Instead, it seems to be forming kind of like a square enclosing that intersection point. Now the square has two vertical sides, and these trace down to the x-axis and tell you two values in the sequence. So this vertical line here comes down to almost a half, and the other vertical line comes down here. I can tell you exactly what those are. Just checking over in my numerics. This vertical line is going down to about 0.5130, and this vertical line is going down to about 0.7995, which means that after a while, this sequence is not converging to a limit, but whether it's bouncing back and forth between two values. So we're getting what's called a period 2 orbit, where instead of converging to one number, we're converging to a cycle. You see this bouncing back and forth between two values for a range of A values kind of between about 3 and 3.4. So next let's look at what happens for A at 3.5. So I'm going to switch A to 3.5. And I'm going to triple the number of iterations that run, so this is going to be a longer movie, but again, it's not over until you see the phrase simulation over at the top. So as you can see, we have some kind of like a box that's kind of heading inwards and a box that's going outwards. And at this point, I don't see much of a change, but it's still running. Okay, so this did move around quite a bit, but after a while, it sort of honed in on 4 vertical lines. So this vertical line all the way to the left corresponds to the number about 0.3828. From 0.3828, we actually travel over here to this kind of inner rightmost vertical line. So from this left line, if you follow the horizontal trajectory across the top, you come over here. This value is about 0.8269. Then we travel left to this kind of second vertical line. That's at about 0.5009. And then we travel to the right again to about 0.875. So this is a period 4 orbit where our sequence doesn't converge, but what it ultimately does is it bounces back and forth between 4 values. So it has like a cycle of 4 values that it repeats. If you're curious if the initial condition mattered, it didn't. So let me change this from an initial seed of 0.1 to 0.9. So here you can see that the first few steps are different, but the long-term behavior is going to be the same. All right, so even though the seed was different, we're still cycling between the numbers 0.3828, 0.8269, 0.5009, and 0.875. So that initial seed doesn't matter. We see the same, kind of like a convergence, but to a cycle of 4 numbers. So this kind of behavior happens between 3 and 4, where we don't get convergence to a value, but we get a 2 cycle, and then we get a 4 cycle. You can actually get all sorts of cycles as you get closer and closer to 4. Let's finish this lecture by talking about what happens if I set the value a to be the topmost bound of 4. Recall a equals 4 was an upper bound for our parameter because as long as a is less than or equal to 4, then the types of values we get when we plug into our recursion live between 0 and 1. So when a equals 4, that means that this topmost y coordinate is exactly at y equals 1. So we cover the full range of potential values between 0 and 1. Okay, so let's look at a few simulations with the parameter set to 4. Let's actually start with the seed of 0.25. So I'm going to let x be 0.25, and I'm going to run this simulation for 100 steps, but as usual, you won't be able to see a difference after a while. There wasn't much to see with the simulation because after plugging our seed into the recursion, we actually landed right on the limit a minus 1 divided by a. So this particular seed produced a sequence which had a limit. That's not going to be the case in general. So let me now take this seed of 0.25 and I'm going to adjust it just very slightly to 0.249. I'm also going to increase the number of steps. So again, this is going to run for a while, but this time you will be able to see that something is happening the full time. So here, as you can see, I only made a tiny difference in my initial seed, but we're getting really different behavior. And this is also not converging to any kind of repetitive behavior. It's not converging to that intersection point. It's not producing any kind of cycle. It's really just going forever. Let me adjust this a little bit more to 0.248. You may be able to detect that the behavior looks quite different, but it's a little bit hard to tell when your behavior is so erratic like this. Okay, so I don't know if you can compare this to the previous simulation, but it is behaving differently. So this is not tracing out a curve which is almost exactly the same as the previous simulation when the seed was 0.249 rather than 0.248. So what we're observing here, where just a tiny change in the initial conditions leads to wildly different behavior in the map, is called chaos in mathematics. Just to give you a working definition of chaos, chaos is like sensitive dependence on initial conditions. Typically, if you imagine running an experiment, you think if I just make a slight difference in my setup, I would only expect to see a slight difference in the results. But with chaos, what we can say is that a slight difference in the setup might quickly lead to very different behavior in the experiment. So that's the notion of chaos here, and you see it with this parameter set to 4. So now we're done looking at the range of values of parameters that I wanted to investigate in this lecture. I think the sequence is really fun to work with. One thing I haven't mentioned yet is why it's called a population model. The reason why it's called a population model is we imagine that we're looking at some population, say in year n, whose initial population is denoted by x naught. Now, this population is living in some kind of ecosystem where it has a maximum capacity of the species that it could possibly hold. So you can think of this range of values 0 to 1 as being how full the ecosystem is. So either 0%, at which case you stay at 0% forever, or perhaps you're at 100% of the possible amount of members of your species you could have. You're kind of oversaturated, so then you die off immediately. Otherwise, if you're between 0 and 1, what your species is essentially doing is this kind of a balancing act. So what happens if you watch the values in the sequence, so here A is back to 2, x naught is 0.8, is we can interpret the behavior of this sequence as what would happen to the population if, say, we started at 80% saturation. That's a little too high, so our population dies off kind of quickly, rapid extinction here, but not quite all the way. So our population goes down quite a bit, at which point there's plenty of resources and the population grows. And whenever it's converging to this number a minus 1 divided by a, you can think of that as like an ideal carrying capacity. So if we start with a very small population, it just kind of grows till it reaches carrying capacity. If we have, let me change a few things here. Let's do 0.3. If I look at a simulation like this, here I start over the ideal carrying capacity, but not dramatically so. So we just kind of die off towards that carrying capacity. Whereas if I start over at 90% of saturation, we quickly die off. Later, when we have higher parameter values, we could see this behavior as a population which never really stabilizes on the carrying capacity, but kind of bounces back and forth between undercapacity and overcapacity. Okay, so that's an interpretation of this model in terms of just a simple population model. We're going from 0% to 100% full. The idea is that this ecosystem is really designed to carry perhaps the exact amount given at this intersection point. Sometimes we converge to that, so our population tends to this idealized number of members of its species. Other times maybe it has something like a period 2 orbit where it's kind of underfull, overfull, underfull, overfull, etc. So that's why it's called a discrete population model. Given that we could think of this as a population over time, let's look at some plots for what the population would be according to the logistic map for different parameters A and different starting conditions. So in this first graph, we imagine that A is 1/2, which we know means that the sequence is going to converge to 0. So if we start with the population level of 0.8, you can see it rapidly dies off towards 0. So this is perhaps spanning over 50 years or 50 weeks, whatever the time scale is. And what we have here is discretely plotted points just connected with straight line segments. It's a little hard to see in this picture because the population dies off so quickly. So let's look at a few others. Now the parameter value is 1.5, which means we get convergence, but not to 0. We're going to converge to a minus 1 divided by a, which is exactly 1/3. So regardless of what our initial population level was, here it's 0.8, over time we would expect the population level to go to 0.3333. In this case, what we observe is that we started with a fairly high level of 0.8, which led to a rapid drop-off. So it looks like we went down to about 0.2, and then from there we grew to 0.3 repeating. You can compare that behavior to how we bounced around those web plots that we looked at earlier. Okay, now let's look at some interesting behavior. So in these plots, the parameter A is 3.2, which means we're no longer converging to that special limit value. And what I've done here is given you two populations over time. The one on the left had a starting level of 0.1, and the one on the right a starting level of 0.12. So there's just a slight difference in their initial condition, but what we observe is qualitatively the same behavior. The numbers are a little bit different, because our seeds were a little bit different. But qualitatively, we don't see that big of a change in what we observe. You could guesstimate from these two pictures what a picture would look like if it started at 0.11. So in both these pictures, what we see is that our population started at a low level. Then there's plenty of resources, there's not a lot of competition, so it thrived initially, grew up, until it stabilized not towards an equilibrium value like in the previous picture, but rather we see two population levels that we're bouncing between. So on the left, it looks like our population could grow up to about 0.8, at which point maybe there's too much competition for resources, so there's a little drop off back down to say about 0.51. I'm not exactly sure what that number is, but I'm just eyeballing the graph. And then maybe there's a little more space for everybody. They bounce back to 0.8. So we get these dueling states that these populations are just going to oscillate between. Notice that compared to like our smooth exponential model or our smooth logistic function, this is a plot of discrete points. Let's increase our parameter now. Here the parameter value is set to 3.5, and again on the left we have a starting level of 0.1 and on the right a starting level of 0.12. Because the seeds are different, there are slight differences in these graphs. You notice them mainly at the beginning, but then both of them trend towards the same type of behavior, and once again you could give a pretty good estimate for what you would expect the graph for 0.11 to look like. In these pictures, we see that the populations don't stabilize towards a limit, nor towards two particular values, but rather we have those 4 cycles where there's a high value, a low value, a medium high, and a medium low. So if you think back to the web diagrams, which one was that like? In none of the pairs of pictures we've seen so far have we seen any clues towards chaotic behavior. So you would look for chaotic dynamics if a slight change in the initial conditions leads to qualitatively quite different behavior. In fact, you would be unable to make a close prediction to what the graph would look like if you were to just tweak the initial condition a little bit. So let's increase the parameter now up to 4. So now that parameter is 4 and I've given you 3 plots. The leftmost one has a starting level of 0.1, the middle one 0.12, and the one on the right 0.14. So while we observe some commonalities in these pictures, they each have moments when the population goes almost all the way down to 0 and then kind of slowly grows back. It would be hard for you to sketch 0.11 or 0.13 based on these graphs because the behavior varies quite dramatically between them. So this is indicative of chaos. A slight change in the seed leads to different graphs. So it's not like a little change in the seed just slightly alters the resulting picture. It can be quite dramatic in this case. And in these populations, we don't have any oscillating behavior. We don't see a limit, nor do we bounce between 2 states or 4 states. If you look at the picture on the left, there are a couple moments when the population is almost entirely full at 100%, and then other moments when it's down to 0, and then there are intermediary values, and it's not really trending towards any one thing. Let's look at one more graph. Here the parameter is still set to 4. I changed the seed to 0.24 just for a little variety, but the main difference here is that the time goes from 0 to 200. So once again, we see features that this graph has in common with the other graphs that we've seen for the parameter value of 4, like those moments when it's close to 0 and then it slowly starts to recover. But based on this, we can't sketch an accurate picture for what it would look like from 200 to 210, how it's going to bounce around. But in this picture, over 200 units of time, you really can't see any kind of trend behavior that this population follows. It's just bouncing around from low to high values in a way that we can't really predict just by looking at this graph. One thing to keep in mind is that we've seen the logistic function. This is the logistic map. The main difference there is that the logistic function was a continuous function of time. So t was not discrete moments in time. So when would you use one versus the other for a population? You would use a continuous model like the logistic function when you have a population where births are occurring in a continual way. The human population is actually like this because there's not a well-defined birthing season. Babies are continuously being born all year long. This logistic map might be more appropriate if you have a species that has discrete moments each year when, say, the birthing season happens. And then the population at the end of that season will influence the following season. So it's like you have a population that changes discretely rather than continuously. Okay, I hope you enjoyed this look at the logistic map. Thank you for your attention.